So welcome to today's lecture. So today we are going to take off from where we left last time, which was message compression via rejection sampling. So we will see how one can actually go from rejection sampling to a covering lemma. Yeah. So here is a quick recap of what we did in the last lecture. So we saw the substrate theorem. Then we used the substrate theorem to prove the one-shot Stein-Slow amount. And then we moved on to a Shannon theoretic topic. So we saw how to do one-shot message compression. So let's recall the main theorems. So substrate theorem part one just gave an upper bound for the hypothesis testing relative entropy. Okay. D epsilon min is less than D1 by 1 minus epsilon. So it's, I mean, this quantity is roughly D1. But D epsilon max is expected to be much bigger. So the upper bound is a much bigger quantity. So that is roughly D1 by epsilon. D1 is the Renyi-1 divergence, which is the Shannon relative entropy. Then the one-shot Stein's lower bound was easily proved by connecting the problem to D epsilon min. So let us say the probability of the good hypothesis, PS, is 1 minus epsilon. And suppose it's a positive constant. Then the probability of the imposter hypothesis QS, okay, cannot be zero. Not just the fact that it is non-zero, there is a quantitative lower bound which you can give, which is the Stein's lower bound. So by definition, it was 2 to the power minus D epsilon min, and by the substrate theorem, we get this bound in terms of the relative entropy. And then we saw an important application of our entropy quantities. So that was one-shot message compression. And for the one-shot message compression, we showed that Alice's message length can be made less than this quantity. So this is basically the max, the smooth max mutual information between X and Y. And then there are some fudge terms log 1 by epsilon. So epsilon is the smoothing parameter. Okay. And the resulting distribution that we get, that I called P dot. So the P dot is not equal to the original distribution, but it's guaranteed to be within 10 epsilon L1 distance to the original distribution.
Shouldn't then the epsilon in the Imax epsilon exponent be 10 epsilon also? Because the smoothing distribution is within 10 epsilon, right?
No. So this I epsilon max, this is epsilon only. The smoothing distribution here is within epsilon, but then there are errors in rejection sampling, so it adds up to 10 epsilon.
So this P dot was the distribution created by the protocol, but
correct.
Okay, I see.
Which is different from P prime. So let me remind you. So P prime is the vector attaining the optimum in the definition of Imax epsilon. Okay. So indeed, P prime is within epsilon of P. Okay, but and the aim of rejection sampling is to achieve P prime of Y given X. Okay. But then there are errors. You see, I mean, I'm only using a finite number of copies of the public coin. So there's a probability that I reject in all iterations. So all these errors add up. And when they add up, I get 10 epsilon. And that calculation is somewhere out here.
No, I remember now. Thanks.
Yeah. So I mean, so this is P hat. P hat is a subdistribution. So then there are various errors out here, right? So this is the probability of not terminating, which has to be bounded by breaking it up into two sums. So this is a slightly clever trick out here, and this makes it 5 epsilon. But this is now a subdistribution. P hat, the probabilities don't add up to 1; they add up to something less than 1. So if you want to make it into a genuine distribution where probabilities add up to 1, the 5 epsilon becomes 10 epsilon. So I hope this jogs your memory.
Yeah, got it. Thanks.
Okay. Any more questions? So let's go on to today's topics. Okay. So yeah. So we are recalling the message compression problem. So recall there is a underlying probability distribution PXY on alphabet X and Y. It's a joint distribution. Now this protocol is allowed the use of public coins. So the public coin C is distributed according to some distribution on the coin register.
Pranab, sorry to interrupt, but I think your mic is, I mean, there's some interference coming in. Your voice is not very clear.
Let me stand of the print. Okay, is this better?
Yeah, that's better. Thanks.
It's probably the wind. Yeah. Okay, so we have this public coin C, which is distributed according to some distribution PC that is independent of PXY actually. So, and the sender Alice gets a sample X chosen from the marginal PX. She wants to send a message which will now depend on her sample X and the public coin C. Okay, just a second. I'm not going to take this call. Okay, yeah, sorry about that. Yeah. Okay. Hello. Yeah, am I audible?
Yeah, yeah.
Yeah, sorry, yeah. I got a call from the director's office, so I have to take that. Anyway, okay. Yeah. Okay. Yeah. So so the Alice's message M is a function without loss of generic deterministic function from a sample X and the public coin C. Okay. And she has to send this message to Bob so that he can generate a sample Y, which will now be a deterministic function of the message M and the public coin C. And the whole thing is, of course, a probabilistic procedure. The probability is involved in the choice of this sample from the outside. Then the probability is coming from the random coin, which is independent of everything else. Okay. So the resulting joint distribution P dot of XY should be close to PX. And the question is, how short can the message be? So we saw that Alice's message can be made less than this quantity, basically I max epsilon. And the resulting distribution is 10 epsilon close to the original distribution. And
So I just have a couple of questions. So, I mean, this
okay,
is
yeah. We proved this by rejection. Yeah, let me finish this paragraph. You're welcome to ask your comment. Yeah, go ahead, Shanti.
okay. So this is like, I mean, just to make things clear. So this public coin C, this is like the some sort of a joint code book that is revealed to both Alice and Bob, that kind of a thing, right? That is what this public coin C is.
Yes and no. So yes, because you can interpret the proof of the noisy channel coding theorem.
Yeah, that's
So that
where
goes
my
by,
intuition is coming from. That's where
yeah,
my
yeah,
intuition is
but,
coming
but that's the yes part, but there's also no part. Okay. So the no part is in fact in the next two lines, right down. So in noisy channel coding, so sure, there's a code book and you can think of the code book as a public coin. Normally it's not explained that way, but yes, you can think of it as a public coin. Okay, but the point is for noisy channel coding, you can set the code book to something, some instance, some sample, and then the average error of the protocol will be less than epsilon,
Right.
averaged over the uniform choice of messages. Okay,
Right.
but here the public coin is required; it cannot be set. Okay, so message compression, you can view it as a variant of noiseless source coding, but there is a public coin. You cannot set away the public coin. You cannot instantiate it to something particular sample and expect that the resulting distribution will be closed. Okay.
So that brings me to my next question. So why do we, let's say somebody told me that, okay, here is a message compression protocol, but the joint distribution that you get, the joint distribution that the protocol creates, that is nowhere near to PXY. Okay. So what is my ask? Is my ask that I mean, my ask is just that I want to compress. Here is a set of messages, and I want to be able to compress as many of these as possible using as few bits. But in the problem statement itself, there is nothing about any distribution, right? The distribution is something that we bring in separately, or is that
no? So so the problem is exactly as written here. This PXY is part of the problem description.
So this is different from the usual thing that Cover and Thomas had, right?
Which problem you are talking about? So this is a variant of noiseless source coding. In noiseless source coding also there was an underlying PX, okay, which is part of the problem description.
Right.
So
right.
yeah, I mean it is not an analog of noisy channel coding. Okay, noisy channel coding, there are some messages that you have to send. Okay, fine. I mean the channel happens to noisy, but let us say the channel is even noiseless. Noiseless channel is also a noisy channel. But there the aim is you have a set of messages which you want to compress and send through a channel, okay, noiseless channel for now, such that they can be recovered. Okay.
Yeah.
So that is different from saying that there is a probability distribution.
Yes, exactly.
Underlying. Okay, so,
exactly.
So that's why I didn't say it's a variant of noisy channel coding. It's a variant of noiseless source coding. So the difference between source coding and channel coding is channel coding, there is no underlying distribution of the messages. There's a set of messages you want to send.
That's right. Okay.
And fine, maybe the best that you can achieve is that not all messages get decoded correctly, but averaged over the uniform choice of messages, the probability of decoding error is less than epsilon. Okay, that's like, I mean, a step back that you're forced to take. But morally, ideally, channel coding would be you have a set of messages and I want to transmit them with probability of error less than epsilon for each one.
Okay.
And for point to point, we can get it. We can even make the worst case error less than epsilon. But for every message, we can ensure there is less than epsilon.
So basically, when we say message compression, essentially what we mean is that we are compressing a distribution. That is, we are sort of finding out the 1 over H min kind of thing. That is, right?
Oh, the H max, the noiseless source coding was
the H max. Right. Okay. Thanks.
Okay. So yes, so message compression is a variant of noiseless source coding. There is a probability distribution which is a part of the problem description. Okay. In source coding, it was only PX, but here it is PX1. Yeah. And I mean, the reason I call it message compression was the naive protocol would be Alice gets the sample X and she sends a sample from Y, PY conditioned on X equal to X. We saw this few slides ago.
Yeah.
maybe Zoom control is covering the screen. Oh, Neha has a comment. Also in random coding, you can choose to give a structure to your code book, for example. Yeah, sure. But I mean, these are the extra fields. So the difference between them, I think, is clear now. Like in one case, I want to send all the messages with low probability of error. Okay, there is no underlying problem distribution messages. In source coding, that's where the word source is there. There's an underlying probability distribution, which is a property of the source. Okay, and I want to, and the noiseless is saying that, I mean, the channel is noiseless, but you can talk of noisy source coding. The point, the reason nobody talks of noisy source coding in traditional information theory is that you can do noisy source coding by combining noiseless source coding and noisy channel coding. Okay,
That's
this is
the
the source channel separation. So we may have more to say about it in our course also, but let's keep it for another day.
So I also wanted to make one more comment. So like in traditional random coding arguments, even though we use randomness, it's just like a probabilistic method thing. So eventually we get a deterministic protocol. But over here, the protocol is inherently randomized because of the shared randomness. So it's a resource rather than a way to prove something.
Correct. Yeah, and the point is, I mean, I cannot say that I can instantiate it finally to some C naught, and then the resulting distribution P dot for that C naught will be anywhere close to P. It may happen that for all instantiations, the resulting distributions are far from P, but averaged over the public coin C, they turn out to be close. Okay, let me give a trivial example.
Right.
Let us say, I mean, I have just one bit, and my two distributions that I'm dealing with are concentrated on 0. There's distribution number 1, and distribution number 2 is concentrated on 1. Okay, the average of this is the half of distribution. Okay, now let us say my coin decides whether to take the first distribution or the second distribution. Okay, but so for each instance of the coin, what I get is a concentrated distribution. It's nowhere close to the half of distribution. Okay, but when I average over the coin, I get the half of distribution. So something like that is happening out here. Is that clear? Why you cannot?
Okay. So basically, P prime X after. So actually, I mean, yeah. So actually, there is a joint distribution PXYC, right? PXYC. There is a joint distribution. Rather I should say P dot XYC, because that is the joint distribution created by the protocol on coin X and Y. Now, once you trace out, once you average over the C register, the distribution that you get, that is guaranteed to be close to XY. But after the averaging.
Absolutely. Yeah. So let me write this.
Okay. So just one comment. So the example that you gave, that suffers from the problem that the support size is very small. But if the support size were large, and in fact, not just support size, if the support size of the coin was large, then we could get some nice concentration properties, right? From some Markov or something like that, and say that, for a large fraction of the coins.
No. It's not in general. I mean, the 2 I can make 2 to the n. No, I can have.
I see. Yeah.
So yeah, unfortunately, this is the best you get.
I see what you're saying.
So I have this distribution P dot XYC, okay, and then the marginal on XY, which I'm calling P dot XY, has to be close. That's the best I can do. That does not mean that I can set C to something and the condition will be close. All the conditions can be passed. Okay, good. Yeah, more questions for understanding. So there's a fundamental difference. I mean, as we study more of information theory, we'll see. I mean, this is a covering type, and the other one, though it will superficially look similar, is a packing type. I've been saying that. I mean, the two things, covering, packing. So all this is covering. So noiseless source coding, message compression. So all this is covering type. And here, I mean, in several of the protocols, we do need the public coin.
I think what Neha said is also pretty important. I mean, this we have seen in our own work, right? That this is channel coding is somehow it's not a resource based thing. It's a, I mean, you have a channel and you have to communicate, but this seems to be a
Yes.
resource. So this PXY is a fixed resource which you have to work with.
Yes, yes, sure, absolutely. Any further comments? Okay. So yeah, so let's see. So then after we have this achievability result, we can apply the substrate theorem. So substrate theorem upper bounds I epsilon max by the Shannon mutual information I divided by epsilon. Okay. And yeah, so we get this corollary. Now you may say that, okay, I mean, what is so great about it? As we'll see later, in maybe a week or so later, this is important applications to computational complexity. So I told you that, I mean, motivation for doing one-shot information theory comes from a deeper study of information theory itself, which is what we are doing, but it also comes from other areas. So one of the areas is computational complexity, and there is a very, I mean, this form is very useful for a certain problem in computational complexity. Yeah.
So Pranav, I'm not able to see the analogy between this message compression problem and like the problem of covering in general. What's
Oh yeah, I'm coming to that. That's what the lecture is about.
awesome.
Yeah. So yeah, actually, maybe yeah. So if, so maybe some of it may spill over into the next one, but yeah, I assure you by Thursday you will see it very clearly. Yeah. So, but before we go on to covering, okay, the paradigm. So let us go back to some comment that Neha made in the last class. So she was saying, oh, like I have taken the probability distribution, the public coin PC. So what did you actually take in a protocol? We just took independent samples from the marginal PY. Said, what if we take some other distribution? Okay. So sure, I mean, you can take some other distribution. Maybe you can do better. We don't know. I mean, you can try to use the other distribution to mimic PY, but of course that's not a good idea. But maybe there is somebody clever who avoids rejection sampling completely. So it turns out that is not the case. So we want to prove an almost matching converse to achievability. So the idea to prove this almost matching converse is to use data processing inequality. So the data processing inequality will be applied for the action of the decoders at the Bob's end. So remember what the decoder Bob was doing? He was mapping the pair n comma c, the message comma coin, to his guess about y. So which was this deterministic function yn comma c. But there are a few obstacles if you think a little bit more about using the data processing idea. So data processing only makes sense for the protocol, right? I mean, in the problem description, there is no data processing out here, which is not obviously. So the protocol is giving me P dot. The protocol is not giving me P. Okay. So for the protocol, yes, there is so you can think of this joint random variable. The protocol is creating a joint random variable on X and C. So there is the sample X that Alice gets, the message she sends, and there's a coin register. And from here, from MC, the decoder applies this decoding function and gets one. So this is the data process. But it occurs at the level of P dot, not at the level of P. But if we want to state our bound in terms of the original distribution Px, why? Because the achievability is in terms of the original distribution, right? And original distribution is a part of the problem description.
We can just use continuity of the distributions, right? For to get around this.
Yeah, but you have to sure. I mean, it is continuity, but remember, in this business, we cannot just say it approaches or something. Remember, we have these fudge terms, and we are tracking them down to the last epsilon. Okay. So sure, it's continuity, but I want to track down these fudge terms, the loss that is incurred by continuity. So, but yes, that's what we have to do. So we need to get around this obstacle of. So we can only apply data processing for P dot, but we have to go from P dot to P because our final bound should be in terms of P. Now the second thing is fine. Let us say we know how to do it. Then we are doing data processing for P dot. But so the data processing will say that I epsilon max, the max mutual information between X and MC is greater than the max mutual information between X and Y. That will be the data processing, okay, for P dot. Okay. And it will all work out if you can show that this is less than log N. I'm putting the approximately because this will not be quite true, but let's say it's approximately less than or equal to log N. M is the, remember, the message register. So this is the number of bits of message. Now, the only way, I mean, this might be true is because C is independent of X. Remember, the public coin is independent of X. So let us see that, I mean, there is some hope of this being true. So this is actually trivial for the Shannon mutual information, which you can work out. You can use the chain rule. So suppose this was just the Shannon mutual information I. You can use a chain rule and first decompose it into the mutual information between X and C. So write it down. Corrected data. Okay, so I have something like this, right? So because C is independent of X, this term is 0. And here, no matter how I condition on capital C equal to small c, the public coin, this is upper bounded by log n because the message n is on log n bits. So that's it. So this shows that this quantity is less than or equal to log. So this is trivial for Shannon mutual information, but unfortunately we don't have such a nice kind of chain rule with equality for I epsilon max. But nevertheless, something like this will turn out to be true. So this is what we need. So is the plan of the proof clear?
Yeah.
Yeah. Okay. Okay. So let's start. So let us look at. So remember, I want to do data compression. I want to do data processing for P dot. So I will look at the max mutual information in P dot between X and Y. So which is just this quantity. Okay. And let us say I'm taking the smoothing parameter to be delta. So I mean, we can later on set delta equal to epsilon, but I just wanted to have a sharper understanding of parameters, so I'm calling it delta. So let P dot prime XY be the optimal subdistribution, okay, which achieves this smoothed optimum. So I know that P dot prime is less than or equal to P dot by the definition, and it is delta close to P dot prime is delta close to P dot. Now, let us define a subset of the sample space Y. Okay, so Y is the subset where Py by P dot Y is less than half. So I know that P dot is okay. So yeah, so I know that P dot is the resulting distribution out here. I know that P dot is close to P. So I would expect that the probability of symbols Y in this set S cannot be too large. So that's precisely what I use. So I know that 10 epsilon upper bounds the L1 distance between P dot and P. Okay, so I use monotonicity of L1 distance. So greater than or equal to the L1 distance between P dot on Y only. I'm just discarding X. Okay. And then I use the property of the L1 distance. So upper bounded by the difference in probabilities the two distributions take on the set S. So the probability given by P dot on S and the probability given by P on S. And now remember S is this property, so I just plug it in and I get that, yeah. So I get this inequality greater than or equal to P dot S. So this immediately says that P dot S is less than or equal to 10 epsilon. And remember P dot prime is a subdistribution of P dot out here, right? So P dot prime of S is less than or equal to P dot of S also, less than or equal to 10 epsilon. So this is the first step to apply my continuity idea. Now let us define another subdistribution, P dot double prime. So we had P dot prime here. Now I'm defining P dot double prime. So P dot double prime is basically equal to P dot prime.
So why was the first inequality to like this 10 epsilon greater than or equal to this thing? That was just.
Oh, this is
okay. The theorem like.
I mean,
we want.
Yeah, the requirement of the problem.
Okay.
See, yeah, my achievability was only giving me 10 epsilon, so I better prove the converse for 10 epsilon.
Okay.
So you can see what is the gap between the achievability and the converse, if any. Okay, so that's all. Yeah. But of course, I mean, if this was epsilon, you put in epsilon and the proof will run through. Any doubts so far? Okay, good. Yeah, so now I cannot work with P dot prime, but I have to tweak it a little bit more. So I'll use P dot double prime, which is basically the same as P dot prime if Y is not equal to S. And if Y is in S, I just zero it out. So basically, I mean, this S is the bad guy, which has to be thrown out in order to do this. I mean, in order to formalize the continuity argument. That's what I'm doing. So zeroing out my symbols X comma Y if Y lies in S. So remember, if Y lies in S, all the X comma Y's get zeroed out. So now, what do I have? So the L1 distance between P dot double prime and P dot prime is less than 10 epsilon.
Actually, I didn't get why S is like a bad set. I mean, like what's so just the set of Y's is that P by P dot is less than half.
Well, so if P dot is close to P, you'll expect that these two are close to each other, right? So
yes,
if the ratio is too small or too large, they are bad. For our purposes, bad will mean too small. It will become clear by the end of this page why we have singled this one out. Okay, so okay, but the first thing is already clear. So once I've defined S this way, I know that the probability of S under P dot, okay, is less than 10 epsilon. Which and then that will further imply P dot prime also has probability of at most 10 epsilon S. But just hang on. So now because P dot prime has only 10 epsilon probability on S, if I zero it out and get P dot double prime, the L1 distance is at most 10 epsilon. So what do I get? I now get that the L1 distance between P dot double prime and P is less than 20 epsilon plus delta. Okay, this is triangle inequality. So from P dot double prime to P dot prime is 10 epsilon. Okay, then from P dot prime to P dot is delta, and then from P dot to P is 10 epsilon. So that is 20 epsilon plus delta. Okay. I repeat, so P dot double prime to P dot prime is 10 epsilon, which we have already here. Then P dot prime to P dot is delta. Okay. And then from P dot to P is 10 epsilon. So it's 20 epsilon. So consider now the subdistribution P prime xy defined. So this P prime is basically the minimum or the intersection of probability distributions. Right? So formally, at the symbol pair x comma y, it is defined by this: the minimum of P dot double prime and the original distribution. Okay, so why am I doing this? I know that P dot double prime is close to the original distribution. Fine, but I cannot say it is dominated by P. I cannot say P dot double prime is less than or equal to P. So the culprit is because I could not say that P dot prime is less than or equal to P. P dot is something that the protocol produces, some great protocol produces. So I have no control on what P dot is. So I cannot say that P dot double prime is less than or equal to P. But by this process, I'm defining P prime, and this is guaranteed to be less than or equal to P. So this is what I have here. P prime is less than or equal to P pointwise. And again, so the L1 distance between P prime and P is less than 20 epsilon plus delta, just coming from here. So this you can figure out by drawing graphs, that nothing else changes. So what have I got by all these exercises? I found a subdistribution P prime, which is close to P, the original distribution, and is less than or equal to P. And more properties, which is in the next slide. So let's look at, so remember, I mean, I'm looking at this Dmax quantity. So what is this Dmax quantity? It's basically the ratio of the joint distribution by the product of the margins. So now I'm going to look at the ratio where the joint distribution is from P prime, but product of the margins is according to P. So I do a little bit of tweak. So I know that P prime, okay, is okay. So I know that P prime is less than or equal to P dot double prime, pointwise, just because of the minimum condition. And I know that P dot double prime, okay, is less than or equal to P prime, right? In fact, P dot double prime is equal to P dot prime for y not equal to s, and it's 0. So this is pointwise less. So so the numerator P prime is less than or equal to P dot prime. I got that. For the denominator, so I have Px out here. Okay. So now note that Px and P dot x are the same. Okay. Why is that? So what is P dot? P dot is the probability generated by the protocol. The protocol is fed a sample x from the outside, and this sample is coming from the good old Px. So P dot x and Px are the same. Okay, and for Py, yes, something might be different. So I just correct for that, and I get this. Now, what do I know? So note that the only y's for which this inequality is interesting are the y's where P prime xy is non-zero. I mean, if P prime of x comma y is 0, then I mean this inequality will be trivially true. And when is P prime non-zero? P prime was defined like P prime is non-zero only if P dot double prime is non-zero. P dot double prime is non-zero only if y does not belong to S. So I know that the y's which appear here do not belong to S. So Ishan, so this will now answer your question. So what do I know about these y's? I know that this ratio is greater than 2. P dot y by Py is greater than, sorry, it does not belong to S, so it is less than. Is it clear, Ishan?
Does not belong to S, so it's greater than half. Okay.
Yeah, so this ratio is less than 2. It's P dot by P now. Yeah, so that's it. So that is the +1 out here. And what do I have about P dot prime by P dot x times P dot y? Now, P dot prime, I know is less than or equal. I mean, I know that P dot prime is the optimal subdistribution in this smoothed quantity. So this should have been delta. So this is nothing but I delta max of x colon y with respect to P dot. That is precisely this one. And then the +1 is coming from P dot y by P. So that's the explanation for this chain of equalities. So you should go back, look at the slides, and figure out each step. Okay, it will be a good exercise. So any questions? Yeah. Okay. So to recap, I mean, you have to first show that at the numerator level, P prime is less than or equal to P dot prime pointwise. Also, y does not belong to S for this inequality to be non-trivial. Then you have to argue that px is equal to p dot x, and then finally you get the first inequality. Now, for the second inequality, you have to argue that this ratio is less than 2 because y does not belong to S. And the first ratio by definition is less than or equal to 2 to the I delta max. So I'll correct that in the notes. This is to I delta. Okay. So now what is this telling me? So look at what I've obtained. So this is p prime by p prime of x comma y by the original px times original p. And remember, p prime is less than or equal to p pointwise, and p prime is close to p. So this p prime is a candidate for smoothing this quantity. The max mutual information between x and y for the original distribution p, and now the smoothing parameter is 20 epsilon plus. So remember, I mean, the smoothing means I take the minimum. Okay, this is a candidate for the minimum. So fine. So this shows that the smooth, I mean, if I smooth up to this level, this is less than the exponent outlet, which is I delta max of x colon y for with respect to p dot. So this connects p to p dot and finishes the first part of our plan. So remember, I mean, we could have only used data processing for p dot, so we are forced to work with this quantity, okay, which is I delta max with respect to p dot. But my final bounds, I want to talk of some smooth Imax for the original p, and this is how I have connected them. But one had to go through all these definitions to find out. And yes, so this is a continuity.
So if I understand this correctly, so what do I want to show? I want to show that for any, I'm just going to recap this thing a little bit to see if I get it. So I want to show that given a protocol which produces a p dot distribution that is close to pxy and also does this, it cannot compress much more than Imax epsilon of xy, or maybe Imax 10 epsilon or something, some fudge factor. Right? Yeah. So that's what I want to do. So to do that, I'm going to say that, okay, I have absolutely no idea what this p dot is. Okay? I don't know what this p dot is, but what I can do is sort of prune. So what happened?
Yeah, go ahead.
Yeah, can you go back to the
you want me to go to this side?
Yes. Yeah, so what I'm going to do is, so I don't have any idea about p dot, but what I can do is I'm going to prune my original pxy, or the whatever this p dot is given. I'm going to sort of do this hybrid kind of an argument which people do in crypto, and I'm going to create a new distribution p dot prime which is close to both p dot and p, right? That's this step, right?
Well, p dot prime is only connected to close to p dot. That's the smoothing that I get for p dot.
Right.
Yeah.
Right, yeah, but there should be another hybrid in the middle, right? Which is close to.
No. So there are several hybrids in that sense. Okay, but the final thing that I want to get is p prime. So I want to prune p to p prime. Okay. So by pruning, I mean I want to lower p to p prime.
Right.
So so I get this, and I don't want to lower too much. I don't want to lose too much. The point is, I want to see. Remember, I want to give a lower bound. I want to say that message length is greater than something.
Yes.
Okay, so that's the converse. So now.
So one question is that even if I had said so suppose that can you just go back to the page again? Sorry.
Oh, you want me to? Okay.
Yeah. So I mean, if I'm cheeky, I'll essentially write down an inequality like this, that this ratio is less than equal to some to the Imax whatever, and the way to define the pruning set, the set of y's that I throw away is precisely given by this. But I could have added any constant here, right? Like Imax xy p dot plus 3 or 4 or something. So the definition of S could have been py over p dot y less than equal to 1/4 or 1/3. Any constant would do.
Any yeah. This is just a proof it was. I mean, I didn't try to sit and optimize it. So I mean, yeah, I mean, you can try optimizing it and see if you can. Okay, but the reason I was going back to the previous slide is, see, I want to prove a lower bound for the length of the compressed message, right? So the only way I can prove a lower bound is via this data processing inequality. Okay, that so where does the message length come in? The message length comes in here. That because C is independent of X, this quantity. Okay, so if it was Shannon mutual information, it would have been perfect. Like this quantity is at most log m. So log m is the message length. So message length is lower bounded by a certain mutual information quantity. Okay, that certain quantity is like after some chain rule or some clever arguments, I can say that it is the mutual information between X and MC. Okay, and then data processing will say that this mutual information between X and MC is larger than the mutual information between X and Y. Okay, so this is basically a very high level proof. So the message length is larger than mutual information between X and MC, which is larger than the mutual information between X and Y. So then I'm done. So lower bound on message length is the mutual information between X and Y, and maybe some smoothing parameters because in one shot. But just this bare argument will not work. So first of all, I mean, there are issues out here because this is not the Shannon information. We cannot use chain rule. So this is one issue, but that is the second part of the plan. But for the first part of the plan, if I want to say that this mutual information between X and MC is larger than mutual information between X and Y, I have to use data processing. The data processing will only work for P dot. Okay, so I can say that this mutual information between X to MC is greater than mutual information from X to Y, true even for smooth max thing, but for P dot. Okay, so then I'll end up proving that, oh, the lower bound of the message length is some mutual information between X and Y in terms of P dot. But I don't care about P dot. I care about P. Right? So I want to get a bound in terms of the original. So to further lower bound the mutual information between X and Y with respect to P dot in terms of mutual information between X and Y with respect to P. So that is the first part of the plan, to go from P to P dot. And that's what we have done here. The mutual information between X and Y with respect to P dot is lower than the mutual, is greater than the mutual information between X and Y with respect to P. But the smoothing parameters change, and all this argument is for the smoothing parameters. To do that, I have to, I mean, if I have to get a quantity like this, I have to prune P. I have to lower coordinates of P to get P prime. But this lowering process has to be sensitive to P dot out here. Okay, because ultimately I'm relating P to P dot. So all this is there to prune P, but keeping an eye on P dot. So that's why S was defined, which relate P to P dot, and so on and so forth. So that is one way of getting some intuition. Yeah. Further comments? Okay, so let's go to the second part of the plan. Okay, so what we showed in the first part is that the mutual information in X and Y with respect to P is less than mutual information with respect to P dot. Now we'll apply data processing inequality on the Markov chain. So X to MC to Y. So we'll get that. Yeah, this should have been delta I delta max. So I delta max. Okay. So the mutual information with X and Y with respect to P dot is less than the mutual information with respect to I mean, is less than mutual information between X and MC with respect to the same distribution P dot. So this is a good old data process. And this quantity I want to upper bound by log. Okay, something finally out here. So this is what I have to do because I don't have a chain. Okay. So remember, this is the smooth max mutual information. So whenever you're doing smoothing, that means you are throwing some sample points away, or you're lowering some probabilities on some sample points. So we have seen. So basically, to identify some bad set, we need to lower probabilities. So here is the bad set that I'm looking at. Okay. So the bad set is S. Okay. It's a subset of the alphabet M times C. So these are those symbols M, C, where this conditional probability with respect to P dot is less than delta by M. So what is, I mean, why is this a bad set? So
this
remember,
is a bad set because if you included this, then your IMAX thing would become greater than log m, right?
Yeah, exactly. So you will see that. So, okay, so first of all, I mean, you can see that the probability of this set under the P dot is at most delta. So easy to see. So fix any symbol for C for the coin. Okay. Now this P dot of n given C is a probability distribution of the alphabet M. Okay. And these are the very low probabilities. So their total mass under the conditional probability is at most delta. So this is true for every C. So now if I sum over all C's also, so if I sum over all C's out here, so I have ended up showing that all these pairs M comma C lie in the set is probability less than 10. So then I know what to do. So I'll now define the subdistribution P dot prime. So this P dot prime is different from the P dot prime in the previous slide. Okay. So this is a subdistribution of the alphabet XMC by this. So this is PX, the good old PX. This is a good old.
Essentially, you're throwing away all the mass. This is all the mass on S. That's it, right?
There's a yes and no again. Okay, so yes, of course, all the masses in S which are there and zeroing out. But when M comma C is not in S, I'm not saying that this is the same as P dot. Okay, so note that this is PC out here. It is not P dot C. So one has to be careful.
No, why would you say P dot C? Because you want to work with the original coin distribution, right? You mean P dot
I
X,
want to work with the original coin distribution, but after all, I'm using a P dot out here. So maybe naively one would say that. And remember, this I delta max quantity is evaluated with respect to P dot, not with respect to P.
Okay, I see.
So there is a case to be made for smoothing P dot.
Okay.
So what will give me this?
P dot X, P dot C. By P dot C, you mean the marginal that you get from the subdistribution P or the distribution P dot XMC. But you don't want to work with that. You want to work with another sort of a hybrid.
Yeah.
That P dot C has been changed to PC, but everything else is the same.
Yeah. So what I know, what I know in P dot is P dot X is same as PX. This we argued in the last slide because X is coming from the
yeah. P dot X is same as PX, and P dot M given XC is the same as what you would get in the original P dot. But what you have changed is the PC here. Instead of PC. P dot C, you have PC.
Yeah. And in P dot C is no longer independent of X because of the actions of the algorithm. So the distribution P dot would have been PX here, then P dot of C given M, and P dot of M given
right.
XC. Yeah. So I'm not doing that. I'm taking PX and PC according to the original distribution P. Okay, so PC is just independent. But now this conditional distribution I'm giving from the protocol. Anyway, the conditional distribution can only be given from the protocol. P dot. Okay. So now what can I say? So okay, so let's see. So P dot prime XMC, okay, is less than P dot XMC, and I have lost how much out here?
No, why is the inequality true?
Yeah, let's do that.
I mean, you would have to you need some kind of condition on the coin, right? To be able to say this. You need a
wait a minute.
Condition on the coin.
Wait a minute. Maybe I was okay. Let's revisit this. So this is so what is P dot doing? In P dot X is as it is, and no. Sorry. I was wrong when I said so. In P dot also it is PX times PC. So let's see what was P dot doing. X is coming from outside. Even the coin is coming from outside. Okay, and then the
no wait. So this is not clear. One second. So what is the definition of P dot? P dot XYC is the distribution created by the protocol, right? That is what P dot.
Well, not just XYC. I mean, I can talk about XYMC. Right.
P dot XYMC is a distribution on these four guys created by the protocol, right?
Yeah.
Now let's track things down. So px x is coming from px. That is a
This is
part
coming
of
from
P.
px. Yeah.
And the coin is coming from some distribution PC, which is independent of everything else.
Yes. So yeah. So that's why it's px times pc. Then p dot will create m given x. In fact, this is a concentrated distribution because the protocol is a deterministic protocol. Okay. So if
So
you
this
fix
is a
x,
point distribution. So this p dot m dot x,
yeah,
this is a point
it's actually a
distribution
point distribution. Yeah.
because it's a deterministic. But that's fine. The main
That's
thing
fine.
is that it's px times pc even for p dot. So
Even for p dot.
you,
Yeah.
you don't need to define a p prime p dot prime separately.
Correct. Correct. Yeah. So this part is the same for yeah. So now you're right actually. So this thing is yes. I don't know. I was confused. So p dot prime is indeed p dot xmc, but restricted to mc not belong to s. It's just that. I'm just spelling it out clearly what the distribution looks like. Okay. Is this clear? So there's nothing mysterious out here. So I'm just throwing away triples XMC if the pair M comma C lies in S. And if it does not lie in S, I'm just fleshing out what is exactly the distribution. So this part is exactly as written, PX times PC, and then this happens to a point distribution, which is not very crucial at this point, but this is how it looks. Yeah, and now, because I'm just zeroed out some things, then P dot prime is dominated by P dot. And again, I mean, the L1 distance between them is at most delta. That's because of this. So now we can now look at the ratio. So remember, we have to evaluate our Imax delta quantity with respect to P dot. So that's what I'm doing out here. But okay, so for the numerator, I'm using P dot prime. Denominator is denominator should be
No, it's correct. It's denominator is px times pc times pm m given c. That's correct.
Well, it has to be with respect to
M given cx, right?
m given cx. Yeah, it has to be m given cx. So there's a mistake out here, but anyway. Yeah. So so the denominator has to be with respect to p dots. This is px pc, then p dot of m given x.
But then we have an issue.
No, yeah, so there's no issue out here. Okay, so of course, I mean, we are only looking at the non-zero guys out here. So this is so I get the same px and pc out here, which cancels, and then I have p dot prime of m given xc. Okay, and this is
pm given xc, but the definition of the set S is, so this is pm given xc.
well, this
with
should,
S has been
yeah,
defined as
this should be m given xc. Yeah, that's all. No, why I probably just forgot it.
So it's all triples mxc such that p dot m given xc is less than delta over m. That's the correct definition.
That's the correct definition.
So this, could you just correct the triple? It should be like m comma x comma c, not m comma c. In the
yeah. Yes. Then this quick question. Yeah, sorry about that. Yeah. Okay, so once we do it, I don't care what the denominator is. Yeah. So sorry, I don't care what the numerator is. I mean, the numerator is mostly zero actually because it's deterministic protocol. But in one case, it might be one. But in any case, the denominator is larger than delta by m, so this becomes m by delta. So what does this tell me? This tells me this I delta max of x with mc under p dot is less than log m plus log 1 by delta. So this is basically the replacement of the chain rule proof. So this finishes the second part of the plan, and we have the following plan: that Alice's message length is larger than the smooth max mutual information, but now the smoothing parameter becomes 20 epsilon plus delta. It's evaluated with respect to the original distribution P, and then there's a fudge of log minus log 1 by delta minus 1. Yeah. Is there minus 1 here? Probably there's no minus 1, it's just minus log 1. And this holds if the resulting distribution P dot is required to be within 10 epsilon. So now look at the achievability. The achievability was the same I epsilon max, but there's a difference in the smoothing parameter. This was epsilon, this is 20 epsilon plus delta. And then there's a difference in the fudge factor. So let's say I take delta equal to epsilon. So this will look like log 1 by epsilon. This will look like minus log 1 by epsilon. So there is a additive gap of log 1 by epsilon or so. There's also a gap in the smoothing parameters. So this looks like 21 epsilon if you set delta equal to epsilon. But up to these gaps, I have got almost matching upper and lower bounds. So this happens from time to time in one-shot information theory. So the converses often have different smoothing parameters. Okay? And there might be additive terms. Note that these additive terms don't depend on the size of the sets involved. I mean, they're just additive terms which only depend on the smoothing parameters. So the additive terms can be different. So this will be the nature of bounds that we will be proving. Sorry, it's a little botched up, okay, but yeah. So this should be X and C. This should be the condition less than delta y, and then the proof will go through. Okay, so questions?
So I just have a comment. So basically, the whole game of proving converses is find bad sets and prune.
Well, the whole game of proving converses, well, proving converses is not easy. Okay, so you cannot say the whole game, but one important tool to prove converses is data processing inequality. But you have to apply it cleverly. Okay, and often when you apply it, it's not. I mean, just applying it in a naive way is not good. So I could have only applied it to P dot out here. Okay, but I need my final answer in terms of P. So then you have to do all these things like pruning, shaping distributions to go from P dot. The point of the nice thing with smoothed quantities is that if you have an entropic quantity with respect to a distribution P dot, okay, but you say no, I want my final answer in terms of a nearby distribution P. Okay, the smooth entropic quantities are smooth. Like you can change the underlying distribution from P dot to P. You just will change the smoothing errors a little. So with the non-smooth quantities, this will not happen. Even if you take Shannon mutual information, if you evaluate with respect to P dot, if you evaluate with respect to P, you get two very different quantities in general, even if P dot and P are epsilon groups. Okay. That does not happen with the smoothed quantities. Okay. So that's a powerful reason to work with the smoothed quantities. And well, I mean, if this looks very depressing, I mean, the point is look at the IID limits. If you took the IID limits, this will go to n times the Shannon mutual information with respect to P. Okay. This will also go to n times the Shannon mutual information with respect to P, the same. Okay. And then people usually in the IID world, they divide by n. If you divide by n, this additive fudge terms, okay, remember they have nothing to do with the dimensions or the sizes of the alphabets involved. Okay, so they have nothing to do with n. So just n will divide this and send it to 0. Okay. So if you're looking at the IID limits, you've got the precise answer that per resource use, the message length is the mutual information with X and Y with respect to the original. And the achievability can be done by the achievability can be done by encoding each copy independently. You just use a protocol for one copy, I epsilon max. And the converse holds true even if you use an arbitrary strategy for the n copies. Even if you do some joint source coding, you're not going to do better than the Shannon mutual function. I mean, you have got it out.
So I have one more comment. So
yeah,
when we do proof converses for asymptotic ID protocols, we never have to shape distributions. The two main tools are this Fanos inequality and data processing inequality, right?
Yeah.
So is that because the Shannon mutual information comes packed with this chain rule sort of stuff, right? With chain rule and data processing. I mean, that's the
Yes.
only thing that seems to be used. So
Yes.
if
So
we had a chain rule for Imax epsilon, then would we still need to do the distribution shaping?
Maybe in some cases, may not be in this case, but maybe in some cases we will.
Okay. But that would have to be chain rule with equality, not the kind
It
of
has to be chain rule with equality, which we don't have.
Yeah. So we have like with inequality as we know now, but okay.
Yeah. And I mean, you're not going to get a chain rule equality. I mean, you're only get to the inequality. The best you can hope for is that the additive fudge factors will not depend upon the set sizes involved. It will only depend on the smoothing error.
Right.
That's
I mean,
the best you can hope for.
For max epsilon, we have the upper bounded chain rule and lower bounded chain rule is unknown, right? Upper bounded is from our
yes. Well, it was also kind of known, but anyway. Okay. Yeah. So further comments. Okay. So let's go to the next part. Yeah. Okay. So Ishan was wondering what we have to do with the covering lemma. So yeah. So now we should slowly start answering questions. So how we are going to go from rejection sampling to covering lemma. Okay. So recall the rejection sampling procedure. So what did we do? So remember, I mean, we wanted to compress down to Imax epsilon, okay, with respect to the original distribution P. So let P prime be the subdistribution attaining the optimum, okay, in the smoothing operation. Remember, Alice got a sample X from the original distribution Px in the outside, and then the coin was IID samples Y1 to Yn drawn from the marginal Py, the good old Py. Then we remember Alice analyzed them one by one. Then with independent private coins, she accepted the ith sample yi with this probability. Okay. And if yi is rejected, Alice proceeds to yi plus 1 and so on. If yi is accepted, Alice halts and outputs I. Okay. And then Bob, who also had the public coin, looks at I and outputs y. And that was the rejection sampling protocol in a nutshell. Okay. I hope everybody remembers it. So this strategy was good for us. We showed that the joint distribution P dot that we get of Alice's input and Bob's output is 10 epsilon close to the original distribution if the number of samples is larger than this quantity. Okay, so the quantity was 2 to the Imax, and then there was this multiplicative fudge, which was 2 natural logarithm of 1 by epsilon. So this we have seen in the last class. Okay, so it's all very good. And we have got P dot close to great. But what we did not study in the last class, and which is important in other applications, is the joint probability distribution of Alice's input X and all the samples Y1 to Yn after the end of rejection set. So what do I know? Suppose Yi is accepted by Alice. I know that the joint distribution of X and Yi is close to the pxy. Okay. So the joint distribution on X and Y of the protocol is P dot. It's close to the original distribution. But I cannot say anything about the other distribution. Okay. Now, if I were a dreamer, I would say that the ideal output of rejection sampling should be this distribution. That okay, there were n of them, n is sufficiently large, n is larger than this. Then I want the chosen sample I or yi to be uniformly distributed over 1 to n. Okay. I mean the I of the chosen sample to be uniformly distributed. So that is the 1 by n. And if the ith sample is chosen, I get something close to the joint distribution. And the other guys are unaffected. The other guys look like the independent copies of the marginal distribution Py. So the notation y sub minus I denotes all the registers yj other than. So this would be the dream that I would like to realize. Okay. So the question is, does this rejection sampling protocol actually lead to this tree? We know, I mean, it gives some I. We don't even know if this I is uniformly distributed from 1 to n, but we didn't care. And for the chosen I, we know it's close to pxy, and that was good enough for message compression. But for other applications, we do have to bother about the other sample nodes. So the thing is that is it close to this?
In fact, it cannot be uniform, right? Because
Yeah. So that
for
is
non-typical eyes, it will be low probability and stuff like that.
well, we're not talking of typical.
No,
things here
by
as-
typical I mean, okay. By typical I mean for I mean, if I is large, that would mean that your coin failed many times.
Yes.
Or if I is super small, that means you succeeded at the very beginning. So when I say non-typical I, that's what I mean.
Okay, sure. You're absolutely right. So that's what, out here. So rejection sampling does not give a uniform. In fact,
So I didn't get this. I mean, why do we want it like?
why do you want this?
Oh yeah, this 1 by n summation. Like.
So there are other applications which you haven't come to, but in the course we'll shortly see that there are other
So
important.
even
No, imagine this. I mean, suppose this were true. Okay, suppose this were true. Then what is this telling you? This is saying that instead of doing all this rejection sampling business, you can start out with a completely product distribution which is px times py1 py2 up till pyn. Okay, and you can pretend that distribution is close to this guy. Okay, now once you pretend that, it simply means that you toss an n-sided coin, and whatever value of I that coin gives you, you just pick up that value of yi. And what this guarantees you is that the joint distribution on x and that I, okay, that is close to pxyi. So that completely gets rid of all this rejection sampling procedure and gives you a very simple algorithm to do the protocol. That's why this is super useful.
Yeah. So very good. That's one very good answer. Yeah. Did you get that, Ishan?
Not quite. But so I mean, I'm just trying to parse this 1 by n. So I mean, like you're saying something, right? That I mean, if we accept y, then we expect that px like xyi. Let's say if I accept sample I, xyi should be close to. I mean, it should be the description would be like very close to pxy. And the others should so yeah. What is like? How do I even read this description which you have written? Like
no. So the question is, what about the others? What about the registers j, where j is less than I, j is greater than I? Okay. So are they?
I think he's not getting the notation py minus I.
No. So notation, the notation is fine. The intuition or no, I mean, I'm not able to interpret it like as in like notation is fine. So this is supposed to be a joint distribution on x and all the yi's, right?
Yes. And
now
yeah. So the point is that this is as okay. So I think I'll just repeat what Shankar says. So on one hand, what did Alice start off with out here? She got a sample from px, and then she got n samples, IID samples, and py. So she started off with n plus 1 independent distribution. So there is one register x, okay, distributed according to px, and then there are n registers distributed according to py, and they're all independent. She starts off with that.
Okay.
And now the question is there? Okay. So Shankar sort of jumped the gun, which you'll see in the next slide. So the question is there some procedure, okay, which will convert this n plus 1 fold independent distribution into something which looks like this? Okay. So what is this? A uniformly random I from 1 to capital N is the chosen one, and that gets correlated to x according to something close to the joint distribution. Okay, and that's it. The others are left untouched. So the others are IID according to py, and moreover, the others are also independent of x and yi. This is what this notation is telling. Okay. So of course, I mean, this is a stronger requirement than what we needed for message compression. And the first question was, does rejection sampling give me something like this? The answer is no, because rejection sampling, first of all, does not even give a uniform I for this joint distribution. In fact, the small i's are more likely to be picked up. A large I, an I close to n, is very unlikely to be picked up because it has to reject so much. I mean, there's a sequentiality in the rejection sampling. So it does not give a uniform I, and nor does it ensure that the other samples are distributed independently according to the original distribution P1. So, okay, yeah. So let us say the rejection sampling picked out an I. So for registers J greater than I, you can imagine that they are independent, okay? But for registers J less than I, remember they were rejected. So if they were rejected, that biases the resulting probability on y1 to yi minus 1. It biases them towards those points which will cause this test to reject. Okay, so you can no longer say that the original distribution of y1 to yi minus 1 is unaffected. Okay, the very fact that you rejected their biases. So there are two problems. I is definitely not uniform, and y less than I. Actually, I should make it more precise. Like from y1 to yi minus 1 are actually biased. Okay. So rejection sampling does not give me this. Yeah, Neha, you're trying to say something.
Yeah, so I don't remember it very well. So these samples y1 to yn, are they coming from the shared randomness between both of them?
So yes. So the
Okay.
yeah.
So when she sends index I, Bob also knows which phi I she's talking. So another question is, why should we even expect this distribution to look like this? I mean, I don't see any reason for the distribution to look like, yeah. Or is it because it has applications if it looks like this, so that's why we are worried about this kind of
yes. So actually, I mean, till a few years back, nobody believed that it will look like this. Okay, this result is a very new result. But yes, so that leads me to the next slide. And so well, maybe more here. Yeah, so let me okay, maybe next to next, but let me come out. Okay, so suppose so this algorithm, the compression algorithm, started off with an n+1 fold independent distribution. So x, 1x, and then n y's. All of them from are independent and drawn from the margins. Okay. Now what Shantan is saying is something amazing. It says that this distribution is actually close to this. Okay. So far I did not make that claim. Okay, I was just saying that is there a procedure which will start off with the n+1 fold independent distribution and come up with something like this. Okay, but Shantan is saying something even more radical. He's saying that you don't have to do anything; it's just close to it. Okay, so suppose this was true. I mean, this dream sounds too good to be true, but we'll see 2 slides from now that it is actually true. Okay, so suppose this is true, then message compression becomes amazing. So what Alice has to do is, okay, so Alice is given X from the outside and she has Y1 to Yn from the public. Alice just tosses a random coin, I from 1 to N. Okay, and then she sends I to Bob. Okay. Actually, she has to do a little bit of tweak for this to be true. I mean, so I mean, for the protocol to actually work, but okay, so let me make it clear. So it is true that this distribution is close to the complete product distribution. Yeah, Neha.
Yeah, so I mean, so you said that Alice will just toss a coin and send that index I.
Yeah, she'll toss a coin, do a little bit of tweak, and then send the index.
Okay. I mean, because just that even Bob can do, right? There's no need to communicate at all.
Yes. So there is a little bit of tweak. Yeah. So Alice, yeah, a little bit of tweak, but the tweak is much less than this. Okay, and it's definitely not a sequential procedure. So Alice indeed tosses a coin I, completely independent of everything else. I goes from 1 to N. Okay, uniform. And then she'll look at the ith sample, do a little bit of tweak, and then send I. Okay, and then Bob will just look at that I and output a yi, which is also available to him. And that will work. Okay. Yeah, and it is true that this distribution. Okay, so here is some reason why it may be true. So if you look at, let's say, the ith term, the correlation is only between x and yi. Okay, it is not between x and y minus I. And the y minus I is anyway independent of each other, right? Now, if I look at some I plus 1th term, then the correlation shifts from x to y I plus 1, and the rest becoming independent. So it's now conceivable that if you do this average, the correlations extending out of x all get smoothed out by this average. So at the end of the day, x cannot have much correlation to any of the yi's. It cannot have much to y1, it cannot have much to y2, it cannot have much. Okay. So that is very roughly the intuition why this is close to the n plus 1 fold product distribution. But again, I mean, it sounds, too preposterous to be true, but that's why it was unknown till maybe 6 or 7 years ago, but it is true.
2014.
2014, yeah. You know that. Yeah, so you should look at when the archive paper came out. Yeah. Okay. Maybe it's 24. Okay, so let's.
Oh, so Pranav, just one more question on that part. So we want to, so we have these samples y1 to yn, and somehow we want to say, I mean, so x is something which is coming from outside, right? Yeah. Which has nothing to do with anything. So we would expect that x is not correlated with any of them much. Okay. So what was the last sentence that you were saying? Actually, I did not fully understand that. You were trying to give some intuition.
Oh, the intuition is, why should this distribution be close to the complete product distribution, px times py1 times py2 up to pyn? Right. Why should this distribution be close to that? The idea is, in the ith term, x is only correlated to y. Okay, it's independent of the yj's where j is not equal to y. Yes. Okay. So yeah, and those yj's are also, I mean, independent of each other. Now, if I look at some other term, let's say y, this I plus 1th term, then x is now correlated to yi plus 1. It's not correlated to y. Yeah. So if you now look at the correlation between x and y1, let us say, they come only for 1 by nth mass. For the others, there is no correlation. If you look at the correlation between x and y2, they come only for 1 by nth mass. For the others, there is nothing. Okay. So if n is large enough, you can now start seeing why you can now pretend that x is hardly correlated to y1, it is hardly correlated to y2, it is hardly correlated. This does not mean that it is not correlated to some joint function of y1, y2, and all, but that's why, I mean, that's why one has to prove something. Okay, but at least you can, if you look at pairwise correlations, you can believe that x is not correlated to y1, x is not correlated to y2, x is not correlated to y3. Okay, so that gives you some idea why this may be true.
Okay, so so there are like these n y random variables, and there is one variable x. Ideally, x is like sampled independently of y1 to yn, and so the distribution of x and y1 to yn, they'll be independent basically. But we are saying that distribution is like close to this distribution, because even over here, the x is not much correlated with the entire vector y1 to yn.
Yeah, so the non-trivial, so the easy part of the intuition, x is not much correlated to y1, it is not much correlated to y2. Okay, the pairwise things. What is not clear is that why x should not be much correlated to the n tuple y1 to yn.
Yeah.
Okay, so that's why I said it sounds too good to be true. That
or maybe we can say something like x is not correlated to many of them, or like it's correlated to only exponentially few of them.
Yeah, you can start off with that, but the point is, see, remember the entropy of px is limited. So the deeper intuition is that the amount of correlation that can leak out of x is limited by the entropy of x. Okay, now if n is really large, let's say larger than entropy, let's say it's even larger than the alphabet size of x. Okay.
Yeah.
There just cannot be too much correlation leaking out of x. Right. And now that gets smoothed out by it. So that's why x cannot be correlated to the n tuple y1 to y.
Yeah, right.
Okay, but I mean, when all this first of all sounds too good to be true. Okay, that's why it was unknown till 2014.
Okay. Yeah,
thanks. But it is true. So I think we'll have only see it in the next class. But yeah, so I will go up to the statement, the formal statement.
So, one more remark. So actually, we see similar kind of statements in adversarial channels, where basically there's a model of oblivious adversarial channel where the adversary is unaware of the message that is passing through the channel, but adversary is aware of the code book. So now over there, adversary will mount some attack. Adversary can try to correlate it with some code words or like bunch of code words. But when a message is picked uniformly at random, adversary cannot correlate the
That's covering lemma.
attack
That's covering
with,
lemma. So this implies covering lemma. That's right. This implies covering lemma, and what you're saying is exactly covering lemma.
Okay,
I mean,
so maybe I'll have to look at your work. It's quite possible that there are close connections between what you're saying and this.
thanks.
I'll have to look at exactly your application, but it's quite possible. This is a very general phenomenon. I mean, because it's so simple, it's very powerful. It can be applied in many situations. Okay, so it's conceivably you can apply it for your adversarial applications. Okay.
Yeah. Thanks.
And yeah. Okay. Okay. So now, as I said, the rejection sampling does not give me anything like this. So that drawback is remedied by the covering lemma, which I mean, to make it very precise, I'll say it's a covering lemma for L1 distance and expectation. What this means, make clear the next slide. But now the N, it increases from what rejection sampling required, which was something like this, to, I mean, rejection sampling required something like this. But now the covering lemma requires a larger N. So you can see that the dependence in epsilon is no longer logarithmic, it becomes quadratic. But still, I mean, it's not bad. It's still a dependence in epsilon. There are no alphabet size factors coming in out. So this strong statement of the covering lemma, okay, so has wide implications, as I said. So one of the implications is, for example, if you go back to the broadcast channel with Martin's coding technique. So if you look at the proof in El-Gamal's scheme, no claim is made that the receivers can decode the actual code word that was transmitted instead of just the block name. So for Martin's purpose, the block name is good enough, but suppose you want to know more, you want to decode the actual code word. So there was no guarantee by the earlier methods, but now if you use this covering lemma, in this sense, in covering lemma is in exactly this sense, then you can guarantee that, okay? And it turns out to be crucial when you look at the quantum version of the broadcast channel, okay? Then this gives better privacy guarantees for the wiretap channel. So this might be closer to what we're saying here. And in particular, because it's a covering lemma for L1 distance, it makes the privacy composable. Composable means, suppose I have a channel and I get some privacy guarantee. Okay, so that's the wiretap channel. I can use this channel as a subroutine in a bigger information transmission protocol. Okay, I can use it as a black box and work with it. So if you look at, for example, the wiretap channel in El-Gamal Kim's book, the privacy requirement was given in terms of mutual information. So those things are not composable. So if you use this wiretap channel as a sub-channel in a bigger information transmission protocol, you can no longer guarantee the privacy holds when there is a lot of side information moving. It's also called privacy side information. But once you have the strong statement in terms of L1 distance, no matter how much side information you put in, it will not matter. So this we'll see as we study more information. So this is a huge issue in cryptography called composability. So the covering lemma for L1 distance gives, composable guarantees, which is very important. Okay, so we stop here. So what is the formal statement we're trying to do? So the first statement is what Shantan was saying. So here is the complete product distribution, X, an independent y1, y2, yn, all chosen from the margin. I claim it is close to this distribution. So an index I is chosen uniformly at random. The ith yi is correlated to X, and the rest are independent and according to the margin. So it turns out it's 5 epsilon close in L1 distance, okay, when n is this large. Okay. The notation y minus y is some the other. Okay. So this is the statement that was proved in 2014 or so, that these are close once n is this large. So it turns out you can give a rejection sampling style proof of the above, a more sophisticated rejection sampling, but we'll see a shorter proof, which is actually the proof in the convex split paper. So the proof will actually use the Renyi-1 divergence or the Shannon relative entropy in a very non-trivial way. And it will in fact prove something stronger. It will say that the relative entropy between these two probability distributions is less than epsilon square, which by Pinsker will mean that the L1 distance is less than epsilon. Now, why am I calling this covering? Is equivalent to the following lemma, which justifies the name covering. So exactly, I mean, the fact that these two are epsilon close can be rephrased like this. So let us see what this means. So let us say I choose n IID samples from the marginal P1, Y1 to Y. So I choose the samples and now they're fixed. Now I look at the conditional distribution X for Y equal to Y1. I look at the conditional distribution for X for Y equal to Y2, so on and so forth. So there are these n conditional distributions that are around. Let's say I take the uniform average. So this is what I'd like to call the sample average. So the sample is Y1 to Yn. Then I take the sample average of the conditional distribution of X. Turns out it is close to the marginal distribution Px. Okay, 5 epsilon close. Once n is this range. So it turns out these two statements are equal. We'll see it next time. And this should look more like covering. So why is this called covering? So the entire marginal distribution was Px. It can be covered by choosing only a small number of samples. So I mean, this n is much smaller than the alphabet sizes. So the true marginal can be covered using a small number of conditions. So that is what I mean by a covering. So we'll see more intuition about it. But yes, so these two are equivalent, and we'll actually prove this. Okay, and okay, now why I'm calling it L1 in expectation. So it says that the sample average is close to the marginal in L1 distance. So this is a much stronger statement than saying that some mutual informations are small. Okay. So that is the L1. And in expectation means if you look at this L1 distance, of course, it's a function of your particular sample Y1 to Yn. The expected L1 distance is less than epsilon. So it's a covering lemma for L1 in expectation. So in the next lecture, we'll also see a covering lemma for L1 in concentration, where we'll say that with high probability, if you take Y1 to Yn, this L1 distance will be, let's say, 5 epsilon plus delta.
That is trivial from Markov, right? From
What?
Markov, this says 5 square root epsilon.
No, I don't want square root epsilon. If I go from 5 epsilon to 5 epsilon plus delta, I want exponential concentration n and delta.
Okay.
That's what I mean by concentration. I mean, I don't mean Markov concentrations. I mean, concentration ideally will be chain of concentrations. Okay. Exponential concentration. Okay. So again, this was something which was not known before. Okay. I mean, in fact, these statements have not explicitly appeared in literature. That covering lemma for the L1 distance, but they become. I mean, they didn't appear till recently, but they're very important if you are trying to prove composable privacy convergence. Okay. So I'll stop here. Any questions? Okay, if not, stop the recording and I'll see you on Thursday.